Hello everyone and welcome to another video tutorial of the EMDLAB software. In this video, we continue the magneto-static analysis of the switched reluctance motor. In the previous video, we generated the mesh and the geometry. Yes. So now we are going to define the solver and apply the boundary conditions, define the winding to calculate the flux density distribution. So, but before starting this topic, let me explain few changes that I did on code. From the previous week that I uploaded the new version of the software in the website, I received a number of great comments. Okay. And based on these comments, I edited few functions. So the most important one was this order for definition of the points and segments. In the previous code, when we add a new point or add a new segment, this function g dot add point, in the previous version, when we add a new point, the first output was the point handle, the second one was point tag. And in most cases, we don't need to have the point handle, and we used this type of programming, right, to ignore the first output and just get the point tag. So I received comments about this one to change the order of these outputs. So we can write point tag, and if we need to get the point handle, also we can write the point handle and get two outputs. So here I changed the order of the outputs. If you don't need any output, just you can write g.addPoint. If you need to get the point tag, you can write this. And also if you need to get the point handle, you can write point one handle. Yes, to get both tag and handle. But we need tags when we define segments and also loops. The same change is applied to edges and loops also. Okay, when we define these geometrical objects. So this was a good comment, and I modified the geometry editor based on that. So you can write your feedbacks, your comments, right, via the contact form of the website, and I try to implement your ideas in the code to improve the code, right? More readability, right? User friendly for future designs. Anyway, so here is the updated code for the switched reluctance motor. We defined these variables. Also, I added the rotor position, the position of the rotor. This is in degrees, right? We need to rotate the rotor when we are going to calculate the electric torque, right, as a function of the rotor position. So Here we have this function for distribution of the mesh density. I will explain it later. The geometry database, definition of the points, segments, and these objects. I defined the stator coil arm, and also let me highlight this function. I set the mesh max length equal to 3 millimeters. Then I change the color of the mesh zones, assign the materials, and right, generate the full geometry. So for the stator coil arm, I use this auxiliary function. Copy, mirror, rotate, mesh zone, right, X. So what is this function? This is the first coil arm that we generated. This is the first stator pole, and this is the stator coil arm. When we use this method, this one, and the input of this one is the mesh zone name, and these two inputs are like this methods. We copy this mesh zone first, and the names will be changed automatically by the method. This will be a stator coil arm 1 and a stator coil arm 2. Then when we rotate these two mesh zones, okay, this is the copy, mirror, rotate mesh zones X. These names will be applied automatically. So this is the stator coil arm 1 1 2 1. For the next pole, we will have the stator coil arm 1 2, stator coil arm 2 2, and so on. We need to have individual mesh zones because we are going to define winding later. This is not like the rotor air pockets, right? That we generate a unified mesh zone. Okay, so we don't need to have individual mesh zones. Okay, so here also I use this method rotate mesh zone to rotate the rotor and rotor air pockets equal to this angle to set the rotor position. Then I generate the global mesh to apply the boundary conditions and also to define the air gap. So let me place a breakpoint here and just run the code. You can see the geometry. And here if I write m dot show mesh zones, you can see the generated mesh for the motor. I changed the rotor position. So how we can define air gap? Definition of the air gap is very important, a challenging task. We can define the air gap mesh using the previous methods that we generated, the stator, rotor, and rotor air pockets, the winding. But I am going to use a more advanced method later. We need that when we are going to perform the transient simulations. Here we have the air gap region, and as you know, the air gap region is important because we have high variations in the value of the magnetic vector potential, the field, right, quantities B and H. So we should have a dense mesh in air gap. We can use the finite element method, or even we can use analytic methods to link the equations of the rotating mesh zone with the stationary mesh zone. So here in this code, I explain the finite element method, and in future I explain more advanced methods. How we can generate the air gap mesh? You know, after generation of this mesh, we can generate the global mesh to attach mesh zones together to have a unified mesh. This is the global mesh. And now I need to find index of these points, right? On outer surface of the moving parts and inner surface of the stationary mesh. I use this method get free boundary nodes, right, on inner circle, and also get free boundary nodes on this circle, right? This is the outer surface of the rotor, and this is inner surface of the stator. Okay, so when I find these indices, I can find the points, the rotating points and the stationary points. Then when I find indices of these points, I use this method, EMDLAB, moving contacts. From the contact library, we have two regions and we need to define a moving contact. First, we pass the indices of the rotating points, stationary points, and this is the number of layers that we need to consider. So when we define this object, we can get its mesh and add the new mesh zone to the mesh database. You know, we can add mesh zones also manually if we generate mesh zones manually. That I will explain it later. This is also an advanced topic when you are going to generate a very fine mesh, a structured mesh, okay, for advanced simulation. Then we add the material, right? And we set the color. So let me place a breakpoint here and run the code. Show the mesh zones. You can see the air gap mesh now. Here I used two layers, okay? And if I reduce the mesh size and increase the number of layers here, for example, 4 layer, let's run the code again. Plot the mesh zones. As you can see, we have a very fine mesh and also a fine mesh in air gap. We have 4 layers of the mesh. So as you can see, we have, right, these freedoms here and manipulate the density of the mesh. That is very good when we are going to calculate quantities in air gap, like the flux density distribution. So let me use 2 layers and this previous mesh size, okay, to compare the results with the ANSYS Maxwell software 3. So when we define the air gap, we select the solver like before, set the properties, and I define the winding. Here, as you can see, the number of turns per coil is 278. This one. This is the peak value of the phase current, 3.6, this number. So I defined this winding considering these coil arms, and also we set the current, apply the boundary condition like before, and solve. So let me place a breakpoint here. Just I want to visualize the winding to check if we are defining the winding correct or not. Here you can see these coil arms of the switched reluctance motor, and here I can write m dot show winding, excuse me, the solver show winding. Here we should write winding 1, the name of the winding. So yes, you can see the winding, and for these regions that the color is blue, the direction of the current is out of the paper, and for the red regions the direction of the current is into the paper, like this one, right? That we have in the ANSYS Maxwell software. So now let's compare the results. If I set the rotor position equal to 0 and run the analysis setup here, I want to calculate the flux linkage, okay, to the phase A and compare with the flux linkage that we calculate in the EMDLAB. So let me increase the font size here. The value of the flux linkage to the phase A is 0.77. Here is the mesh length also in the ANSYS Maxwell. And here I set the rotor position equal to 0. Let's run the code. Here you can see the flux lines, okay? And if I calculate the flux linkage S dot eval, the flux linkage for the winding one is 0.78. Okay, so let's change the rotor position and repeat the simulation. For example, the rotor position equal to 5 degrees. Analyze. I want to check the numbers. Here the material is M530 50A. I used the same material here for the laminations. So for this new position is 0.74. We can change the rotor position here. 5. The value is 0.73. Acceptable. Let's rotate it 10 degrees. Repeat the analysis. Also in MATLAB, change the position. Yes, you can check the flux lines, the flux density distribution, this saturation that we have here. The value of the flux linkage is 0.58. Here is 0.59. Okay, so if I consider the completely unaligned position, this one, and repeat the analysis, also I can compare the numbers. So this is the completely unaligned position, and here is 0.149.15. Here is also 0.15. So we did this comparison, and you can repeat the code to compare the results. I will upload the new code and the modified package in the website so you can download and try this updated code. So the package is in progress, and you can write your comments, your feedback, right? Like this one to improve the code. So how we can have a, a smart mesh? As you can see here, we have these mesh zones, and we have this air gap. The thickness of the air gap is low. We need to have a high quality mesh in air gap, but we don't need a high quality mesh here in the back iron of the rotor or the back iron of the stator, right? If we use a very dense mesh for all regions, the simulation time will be high. How we can have a fine mesh in air gap, but a coarse mesh here? We can control the mesh density by defining a mesh density function. Okay, so let's compare. If I reduce the size of the mesh here, for example, this one, set the mesh max length, and also let me ignore this standard refinement. I want to use 0.5 millimeter for all regions. Okay, and here the position equal to 5. Let's run the code. So as you can see, we have a very dense mesh. You can see the solution. Okay, what is the total number of mesh elements? Here I can write m dot ne. Total number of mesh elements is 111,000, right? A high number of mesh elements. But we can solve the problem in MATLAB in, right, a very short time. So how I can control the mesh density? This is the geometry. And for us, the air gap mesh is important. I can define this function. If you consider the cylindrical coordinate system, this is r, right? The distance of each point from the origin. I can define a function f mesh that is actually a function of the r, and by this function I can control the mesh density, right, in the radial direction. So here I can use this linear function like this one. So this is the r, and this is the mesh size, the y-axis. So here, let me delete this one. Okay, I want to consider this. When the r is equal to ISD divided by 2, we have the air gap. So I want to use a fine mesh here, for example, 0.4 millimeter. And when we are here, OSD divided by 2, we can use a quartz mesh. So here I can consider 2 millimeter, 3 millimeter, 4, but I use a more practical number. This is the width saw, the stator yoke, right? So I consider the mesh size here equal to width saw the stator yoke divided by 2. And when we are here, D shaft divided by 2, we can use this quartz mesh. We can use this size, width saw the rotor yoke divided by 2. So by defining this function, we can handle the quality of the mesh, the density of the mesh. Here, I defined this function. This handle function is a function of R, and I use this one-dimensional interpolation. So if I run this, and if I define R equal to linear space from global variable D shaft divided by 2 to global variable OSD divided by 2, consider 1000 points, plot R and F mesh, that is a function of R. So you can see this function, right? The density of the mesh. So in air gap, we will have highest density. So when we define this function after generation of the geometry, we can use this method, set mesh length by radial function. This is the function handle. Okay. So when I use this method, here is the mesh size in air gap, for example, 0.4, and I can run the simulation. So in the previous case, the number of elements was this number, and I am going to check for the new case. So now if I run the code, as you can see, we have this mesh in air gap and this quartz mesh in the back irons, right? So here you can see the mesh growth, right? That we have a perfect mesh here. And here the number of elements is 20,000. So we can solve this problem much faster when we do the parametric analysis, parametric calculations, and we need to run this M file thousands of times, right, for optimization. So also you can plot the B vectors on central elements and also use other functions. You can check the flux density vectors, right? We have a high variation here in air gap. Okay. So anyway, you can repeat this analysis type, and in the next videos, I will explain how we can calculate the static torque curve and explain other methods. Okay. So we have this structure to analyze electric motors, and we will use the same procedure to analyze other electric motor types. Thanks for watching.